There are essentially two things that happen inside a nuclear reactor. The reactivity which generates power either goes up or it goes down.
Ultimately, the reactor core sits down in here, produces all the heat that basically makes all the steam that makes all the power.
If you were seeking for alien intelligence, looking for a convincing signature of their activities from across the universe, you'd have a few alternatives. You may look for sentient radio broadcasts similar to the ones humans began emitting in the 20th century. You could check for artificial lighting at night, such as what our cities and towns have visible from space. Alternatively, you may hope for a technological breakthrough such as a generation of particles such as antineutrinos in a nuclear reactor. After all, it was through this method that we first discovered neutrinos, or antineutrinos, on Earth. But if we choose that last option, we might deceive ourselves because scientists have shocked the world by announcing the discovery of a nuclear reactor long before humans ever existed. Where is this old nuclear reactor? Who designed it, and how does it work? Join us as we investigate scientists' latest discovery of a 2 billion-year-old nuclear reactor that has the potential to transform everything. Nuclear energy is utilized to produce electricity as well as power weapons. It is created as a result of nuclear reactions such as nuclear decay, nuclear fission, and nuclear fusion. Today, nuclear power plants produce a large share of the electricity generated by nuclear fission of plutonium and uranium. Nuclear power reactors provide about 10% of the world's electricity, and nuclear power facilities provide 20% of the electricity in the United States. Nuclear energy is the most environmentally friendly energy source. It not only provides electricity, but it also allows for space exploration using radioisotope power systems. Radioisotopes also aid in tumour detection, cancer treatment, and camera imaging. They can detect traces of paint, glass, gunpowder, tape, lead, and poisons, which assist in criminal investigations. Furthermore, radioisotopes have an impact on agriculture by reducing insects that cause agricultural damage. However, this 2 billion-year-old nuclear reactor alters everything. 2 billion years is a long period, especially for humankind who struggle to live to the age of 100. However, in the broad perspective of things, that is not a long period in the vast universe. In fact, there is proof of events occurring billions of years before you and I were on the scene. One such occurrence is a nuclear reaction, which powers the reactors that power many portions of the world today. Scientists were perplexed when they uncovered evidence of a nuclear reactor that existed billions of years ago in Africa. Nuclear-related issues frighten many people because of the massive disasters linked with them, which have claimed countless lives and made vast swathes of land unusable for various human activities. Nuclear power opposes a movement to discourage nuclear energy development initiatives in the aftermath of the Chernobyl and Fukushima tragedies. However, nuclear energy is a dependable form of energy that, when properly deployed and maintained, can power a country inexpensively. All nuclear power plants operate on the same basic principles. At the core of nuclear power facilities are nuclear reactors. They confine and manage nuclear chain reactions that generate heat via a physical process known as fission. That heat is converted into steam, which powers a turbine to generate energy. According to what you have just learned about nuclear reactors, they are a contemporary innovation, which is why they made headlines throughout the world when scientists said they had discovered a nuclear reactor billions of years old. What precisely is going on here? This will send us to Oklo in modern-day Gabon, Africa. Oklo is a region in Gabon near the town of Francevilla. For 40 years, France mined uranium in Gabon, which was used to create energy in France and other European nations. However, the uranium resource has now been depleted and the mines have been shuttered. Mine reclamation work is now taking on there. What cannot be taken away from Oklo is the possibility of hosting the world's first nuclear reactor. In reality, Oklo possessed not one, but 17 nuclear reactors. It all began in 1972 when physicist Francis Perrin witnessed something that he thought was impossible. He was inspecting a black bit of radioactive natural uranium ore collected from an African mine in a nuclear fuel processing facility in the south of France. the high-grade ore contains a smaller amount of uranium-235, according to his study. While the proportion was just slightly lower, it was enough to make scientists question whether anything was amiss. The first answer a physicist worth their money would provide is that the uranium did not originate naturally, and they may not be incorrect. The fact is that natural uranium currently includes 0.72% uranium-235. So if you were to extract uranium from the Earth's crust, moon rocks or meteorites, you could bet that this is what you would discover. However, the uranium recovered at Oklo was just 0.717% pure. That could only happen if the uranium went through the process of fission artificially, or if part of the uranium-235 isotopes were caused to split in a nuclear chain reaction, such as in a nuclear reactor. To his amazement, additional analysis by Perrin and his colleagues verified that the uranium ore was entirely natural. Even more perplexing, they identified a footprint-efficient product in the ore, implying that the uranium ore was natural and had gone through fission. Right in front of them was proof that natural fission had happened over 2 billion years ago. By this point, the scientists had established that the uranium came from Oklo in Gabon, and their curiosity had been piqued. Of course, there is no evidence of people being on Earth 2 billion years ago, even if there is no proof that humans understood about nuclear processes or how to harness them at the time. How did the uranium in Oklo manage to fission like it would have in a contemporary new nuclear reactor with no human intervention? When most uranium decays, it produces 3 neutrons. If one of the expelled neutrons collides with another uranium atom, the atom also decays, resulting in a chain reaction. However, in most uranium rocks, either there is insufficient uranium to fuel the chain reaction, or the decay is too quick for a chain reaction to occur. So the scientist's job was to figure out how the conditions at Oklo were favourable to a chain reaction. So how much energy was generated by Oklo's naturally occurring nuclear reactor? To be honest, the power output was moderate. The average output was 100 kilowatts, which was enough to power around 1,000 light bulbs. While that may sound amazing, a commercial pressurized boiling water reactor nuclear power plant generates around 1,000 megawatts, enough to power approximately 10 million light bulbs. The fascinating thing about Oklo's natural reactors is that they spontaneously began running roughly 2 billion years ago and have continued to operate in a steady way for up to 1 million years. Aside from that, the nuclear fission that occurred in these Gabon reactors created masses of radioactive materials that were safely kept for 2 billion years. Isn't this proof that long-term geological storage of nuclear waste isn't impossible? We just need experts to go examine outflow and see how we can increase our ability to store nuclear plant waste. The Oklon fission reactors are the only known examples of a natural nuclear reactor on Earth, but the method by which they occurred leads us to assume that they may occur in a wide range of locations and elsewhere in the universe. When groundwater inundates a uranium-rich mineral deposit, fission reactions can occur, with U-235 breaking apart. The groundwater works as a neutron moderator, enabling more than 1 out of every 3 neutrons to collide with a U-235 nucleus, so prolonging the chain reaction. Because the reaction only lasts a brief period, the groundwater that moderates the neutrons evaporates, bringing the process to a halt. However, without fission, the reactor naturally cools down, enabling groundwater to return. Humanity, like an amazing detective, has been able to compute the particular time frame of the reactor by measuring the quantities of xenon isotopes that become trapped in the mineral formations surrounding the uranium ore deposits. The reactor would reach critical for around 30 minutes, with fission continuing until the water evaporated. There would be a cooling period of around 150 minutes, following which water would flood the mineral ore again and fission would restart. This 3-hour cycle would continue itself for hundreds of thousands of years, until the ever-decreasing amount of U-235 hit a low enough level, below the 3% limit, to prevent a chain reaction from continuing. At that moment, both U-235 and U-238 could only decay radioactively. Looking at the Oklo sites today, we discover natural U-235 abundances that are 0.44% to 0.60% lower than their typical ratios. Although the natural abundance is extremely low at 0.720% U-235 compared to 99.28% U-238, the Oklo samples only show U-235 abundances ranging from 0.7157% to 0.7168%, all significantly below the typical value of 0.72%. The only naturally occurring reason for this mismatch is nuclear fission in some form or another. When combined with the xenon, neodymium and ruthenium data, the conclusion that this was a geologically generated nuclear reactor becomes pretty much unavoidable. Based on this information, we may conclude that nuclear reaction rates and hence the values of the constants that control them were the same 2 billion years ago as they are now. Finally, and probably most significantly for understanding our planet's natural history, we can take the ratios of the various elements to calculate both the age and composition of our planet at the time of its formation. The lead isotope and uranium isotope levels indicate that 5.4 tons of fission products were created over a 2 million year period and around 2 billion years ago, in a 4.5 billion year old Earth. Both U-235 and U-238 are created when a supernova occurs and neutron stars collide. We know from researching supernovae that they produce more U-235 than U-238 in about 60-40 ratio. If all of Earth's uranium was formed by a single supernova, that supernova would have happened 6 billion years before Earth's origin. A spontaneous and natural nuclear reaction can occur on any planet as long as a rich vein of near-surface uranium ore exists with a larger than 3:97 ratio of U-235 to U-238 mediated by water. These conditions might develop at any moment, and as long as few enough half-lives have elapsed relative to the decay duration of U-235, the detection of reactor antineutrinos from another world could imply a natural nuclear reaction just as readily as it could suggest the presence of an intelligent, technologically sophisticated civilization initiating their own nuclear reactions. Let us know what you think about these naturally occurring nuclear reactors in the comments section below.